All right, everybody. Wrong intro. I'm getting ready. Welcome to Tuesday. Welcome to Tech Tuesday. And we're going to talk. This is IAEI News Live. And we are going to talk about ampacity and ampacity of conductors. And I will add, we're really going to be talking about the ampacity of a circuit. So let's talk ampacity, and it all starts now. All right. Man, I don't know about you guys, but what a day it has been. I hope everybody had a great weekend. I was on the phone on Monday, yesterday, and I had a gentleman who was from England and somebody from Canada and somebody else. There was people from a global, and I said, I hope everybody had a great July 4th. And a few of them says like, oh, we don't have a July 4th here. And I was like, well, wait a second. What does your calendar go from July 3rd to July 5th? Because I don't care what part of the world you're in, you have a July 4th. I just hope it was a great day. But in any case, welcome to IAEI News Live. And I want to talk about, I want to do a deep dive on ampacity. I was modifying this PowerPoint up until a few minutes ago because ampacity is not an easy topic. I'm telling you, it is not an easy topic. So whenever you think about whether or not, there we go. If you're sitting there thinking about, well, you know, ampacity is simple, I would beg to differ. It's not a simple topic. So I'm hoping that we have a good, engaging discussion. We got Steve Spiker here. Steve says, also have ambient. Yes, they do. Yeah, circuit breaker, overcurrent protected devices depend upon the ambient and elevation too. And Steve, the X to R ratio. So, and rarely do people even look at an X to R ratio of the circuit, but that could be a good topic for a different session. And hot ambience, yes. And then I will, you know what, Steve, I am going to do a session on just that. So thank you for bringing it up. All right, happy Tech Tuesday. Jason Doty in the house. Panel 10, represent. All right, and then Michael Hofkin, great, thank you for being here. We got Don Gannier, thank you, sir, for being here. Laurel, we got research in the house. Keith Wilson, and then finally, but not least, David Engelhardt. All right, so let's talk. We're going to talk, and hopefully I got this right. Hey, it worked. Perfect. I don't know why, for some reason, when I go into display mode, I don't know what's going on my computer or PowerPoint, but it rearranges everything. But at least I got this right. So let's talk about ampacity. Now, what do we know from Article 100 is ampacity is a defined term, and it's based upon conditions of use. Basically, the definition tells us that it's the maximum current that a conductor. The term ampacity focuses on the conductor. Hey, Felix Sandoval in the house. So when we say ampacity, we're talking about a conductor's ampacity. And I will argue, and we know that it's the conductor's ampacity based upon conditions of use. There's no ampere rating. There's no allowable ampacity, all that good stuff. We've made some changes over the last couple code cycles. But I'm going to basically, I want to introduce a different term to you guys and gals out there. I want to talk about what I think the discussion for our session today is really going to be around a circuit ampacity. And circuit ampacity is not a defined term. We indirectly apply circuit ampacity. We indirectly calculate a circuit ampacity because first you have the ampacity of the conductor and what the conductor itself can carry, 24 hours a day, 7 days a week, twice on Sunday. That's what the conductor can handle based upon the conditions of use. But then the moment that you put it in a circuit, now you've got to think about both ends of the conductor, where the terminations are, and there may be additional limitations placed upon the overall ampacity of the circuit. Now, circuit ampacity is not a defined term. I'm saying I think that we need to think about the overall circuit ampacity differently. And I'm going to talk about that as we go through our discussions here today. All right, so there we go. A little bit brighter. All right, so I'm introducing a new term for our discussion for thinking about the overall ampacity of the circuit. Hey, we got Willie Snyder in the house. We got Chris Folan. Wait, man, we got a bunch of stuff going on. Okay, hold on. Tom would love to hear about conductor ampacity, derating and cable. Oh, not maintained. All right, I will try to cover that, Jason. I will try to cover that. Laurel says under the conditions of use without exceeding its temperature rating. So that is right. So we got under the conditions of use. So conditions of use are very critical. And Chris Folan is good morning. Welcome to the shop. Willie Snyder, smash that like button. Welcome to the program, Willie. I'm more concerned about low temperatures. Based upon one brand's info, a 400 amp breaker installed outside will have a 500 amp trip point for 5 months of the year based upon the average highs. We are going to talk about that one. I'm telling you that, Steve, that's a really good question. All right, so let's get back to our discussion in hand. I'm introducing a new term. I'm going to talk about circuit ampacity in addition to just the conductor ampacity. Now, these are the articles we're going to be thinking about. I didn't put, you got to think about Article 210, 215 for feeders, 230 for services, 240 for overcurrent protection. And I didn't finish this slide, so I'm going to add some more of those. In fact, I'm going to do that right now. Whoa. I am going to, see, I don't know why that does that. Look at that. There we go. All right, so I'm going to do, this. I'm just going to write these in. Article 210, 215, 230, and then Article 240 for overcurrent protection. Those are just some of the references I know we're going to be pinging during our discussion today. Now watch, I'm going to do this. Watch when I do this. Watch what happens. It worked. I don't get it, but it worked. All right, so 310.4. I want to go to 310.4 is a very important section in your journey for determining the capabilities of the circuit, because we have to understand what conductor we're using and what the capabilities of that conductor are. So if you look at table 310.41, I highlighted just two, I would say, of the common. THHN is a very common insulation. It tells you where it can be used, and it tells you the operating temperatures. So, and what I like about this portion of the table is that it shows you that a THHW has a 75 degrees C maximum operating temperature when it's in a wet location, and it has a 90 degrees C operating temperature when it's in a dry location. That maximum operating temperature is going to be important when we start calculating and doing our derating, right? Or ampacity adjustments. We do those adjustments off of the 90 degrees C or the column of the insulation. If I have, for example, a THHW and it's in a wet location, I can't use 90 degrees C. I have to use 75 degrees C as the capability for that conductor for that application. Tells you what the insulation is good for, tells you the range and gauge or KC mils, the thickness of the insulation, and the outer covering for the installation. So for that conductor. So 90, this table 310.41 is going to be very important whenever we start our journey. We have to understand what it is we're doing, all right, and what we're dealing with. All right. 310.16 ampacity of insulated conductors. We're going to be referencing that section. That's going to be, now I didn't know how to put this. I put this in reverse order because here's my point on this one. 310.15 and 14, I can operate a couple different ways when I start adjusting for conditions of use, but typically what I'm probably going to start around is 310.16 and help us understand what's in that table. Then we'll start referencing the other two sections, all right? So if I look at table 310.16, the very title of the table tells me that the values of current, the ampacity values that are in this table are based upon a condition of use. And I have an established condition of use for these ampacity values. That's why we say it's not a rating. We don't have an ampacity rating of a conductor. We have an ampacity of a conductor, which is based upon conditions of use. In this case, we know that the table includes the ampacity values when you have an insulated conductor with not more than 3 current carrying conductors in a raceway, cable, or direct buried. And if you go to the, I didn't put the note in here. If you go, let me pull it up on my iPad. If you go, I have to use fill my password. It uses my face. And I go to NFPA 70, and I go to Chapter 3, Article 310, 310.16, bada bing, bada boom, bada bang, 310.19, 310.18, 17, grasshopper, there is 310.16. I'm going to go down to the tables. Look at this. Oh, I've got a new one. Oops, a daisy. All right. So if I look at this notes section, it says right here, section 310.15b shall be referenced for ampacity correction. I hate when that happens. 310.16. I got a phone call. All right, I'm going to go maximize, expand table. I go always down to the bottom. There we go. Shall be referenced for ampacity correction factors where the ambient temperature is other than 86 degrees Fahrenheit. So it tells me that this condition of use up at the top, it says no more than 3 current carrying conductors in raceway, cable, or earth. And at the bottom, it tells me with the temperature of 86 degrees Fahrenheit. So I know that these values in this table have a condition of use, and I've established the number of conductors in a raceway. I've also established the ambient temperature for the application. Up. There we go. So let's go back to this. The other thing that I've established in this table is the insulation temperature rating of the conductor. So I have a 60, 75, and 90 for copper, and I have the same for aluminum. There's my insulation type. So remember, in that first table in 310, we had like THHW and THHN. We had both of those conductors that we talked about. Those are the insulation ratings, and those mean something. So for me to determine, now I know I have a 90 C common, and I have THHW, but when I go back to that table, I'll recognize the fact that THHW has a 75 C when it's in a wet location, 90 C when it's in a dry location. So you've got to be careful when you're using the table, when you're using these insulation ratings. You got to understand the application. Nihad El Sharif, welcome. Welcome to straight from Egypt. We've got Egypt in the house. Cairo specifically. All right. So THHW, THHN, you got USE2, XHHW, all these things. And we can have a whole nother discussion on what all of those letters mean, and etc. But in any case, we know that those insulation types are going to be important, and we can go back to that table, previous table, and see how to use those, right? And that would be 310. I think it's 310.4. Table 310.41 are conductor applications and insulations. That gives you all of the different. XHHW is 90 C in dry and damp locations, 75 C in a wet location, etc. All right, so, and then the next one is your copper or aluminum or copper clad aluminum. You know, copper clad aluminum has been around for a while, and I know it's been heavily debated recently. And hey, and you know, the 2026 code cycle is going to give us that 10 amp circuit for some applications, which is somebody was happy over that. All right, and then you go to the conductor sizes are on the left-hand side. The star basically tells us section 2 to reference section 240.4D for the conductor overcurrent protection limitations. So when it comes to conductor protection, you're gonna, for those small conductors, remember we got to go back to 240.4D. Beautiful. Okay. There's our conditions of use. So those ampacity values are based upon. Now, that's an important thing to remember. The values in this table, if I have no more than 3 current carrying conductors in a raceway, and it's an ambient of 86 degrees Fahrenheit, a number 8, I'll go with a number 8, can handle 90 C insulation. Say it's a THHN. I can handle 55 amps on a number 8 forever. I'm not going to damage the insulation. I can handle up to 55 amps for that 90 C insulated conductor. That's an important thing to remember. This gives me, based upon the conditions of use, if I meet those conditions of use, I know what I can handle indefinitely. If I change those conditions of use, if I have more than 3 current carrying conductors, if I am at an elevated or a lower temperature than the 86, I will adjust these values. I may be able to get more or less current to pass through those conductors without damaging the insulation. That's the ampacity of the conductor, which will be based upon the conditions of use. All right? And we will talk about the conditions of use. So let's, before we leave that, I did not put as much in here as I probably should have. Wow, that's pretty bad, Tom. My glasses are so filthy. All right, so what I want to do is I want to take a look. We said 310.14 talks about the ampacity of conductors. And in there, they tell you about you can, use the tables. You can do some things based upon, wow. I did all that cleaning, and now I know why they're dirty, because, whew, man, that's a real strong one. I need really small letters for that one. Hey, there we go. Wow. Welcome. All right. So 310.14 tells you ampacities for conductors are permitted to be determined by the tables, or you can calculate those, and they give you some equations. So where more than one ampacity applies for a given circuit length, the lowest value is used. So we know we have to use the lowest value. We have temperature. You can't use a conductor in a manner that his operating temperature exceeds that designated for the type of insulation, etc., etc., etc. Then in B, engineering supervision, they give you the equation. So that's all 310.14 is going to tell you. 310.15 is where we get into the correction factors. So 310.15 tells us that we have ampacities for conductors shall be specified in the table, and you modify them based upon 310.15 A through F. All right, so it tells us under engineering supervision, ampacities of sizes not shown in ampacity tables, so you can go beyond the ampacity tables that are there. So when you have the right qualified person doing the calculations. The temperature and correction and adjustment factors are applied to the ampacity for the temperature rating of the conductor. That's why it's important to, let me see if I can do this. So here, that's why this statement right here is why it's important. And you guys got to get an NFPA link. I'm telling you, NFPA link is the bomb, all right? Absolutely awesome. The temperature correction and adjustment factor shall be permitted to be applied to the ampacity of the temperature rating of the conductor if the corrected and adjusted ampacity does not exceed the ampacity for the temperature rating of the termination. So if the corrected and adjusted ampacity does not exceed the ampacity for the temperature rating. So what that's telling you, so John McCamish and I had a discussion today on that very statement. It says that the adjusted ampacity does not exceed the ampacity for the temperature rating. So what that's telling us is that when I go into the table 310.16, I'm using it for two things. One is to determine the ampacity of the conductor. The other is for the ampacity of the circuit. And if I'm landing in 75 degrees C equipment, I can't exceed the 75 degrees C column. So if I calculate the ampacity and the ampacity is greater than what's in the 75 degrees C column, the overall circuit ampacity is limited to what's in the 75 degrees C column because of the equipment I'm landing in. Okay, so that's an important thing to remember is I'm limited. My limiting factor is not the capability of the conductor. The limiting factor is going to be the capability of where I'm terminating the conductor. I've got two ends. And whichever is the worst case, if I go into 90 degrees C, and we're going to do an example, if I go into 90 degrees C versus 75 degrees C on either end, the limiting factor is going to be the 75 degrees C equipment. I'm going to limit the amount, the ampacity of the circuit, not the conductor, because the conductor has a higher ampacity based upon its conditions of use. But the ampacity of the circuit is going to be a lower value based upon the 75 degrees C equipment and based upon the 75 degrees C column. Don Ganir says, whoa. Yes, Jason, the weakest link wins. Don't forget about 310.14a2 exception. 310.14a2 doodar exception, where different ampacities apply to portions of a circuit, the higher ampacity shall be permitted to be used if the total. Yes, that's a good point. And where this is used, Dawn. So he's talking about this exception right here, where different ampacities apply to portions of a circuit. The higher ampacity shall be permitted to be used if the total portion of the circuit with lower ampacity does not exceed the lesser of 10 feet or 10% of the total circuit. So what we're doing there is we are, if you have a portion of the circuit that, say, is in raceway or in a high temperature, elevated temperature, that's a good example. I'm going through an area that has an elevated temperature, and I do my ampacity calculations based upon the conditions of use for that elevated temperature. If that distance that I'm passing through is less than 10 feet or 10% of the circuit, the lesser of either of those, I'm good to go. I don't have to worry about that value. So very good point, and very important point to highlight. Jason, the weakest link. Yes, you are the weakest link. We ought to do a game show for that. So in any case, let's go back. Let's go back to this. All right. Oh, no, I didn't want to go into determinations yet. I'm in 310.15. So we said, so 310.15 is where I'm going to find all of my adjustments. 310.14, 310.15. So if I go to 310.15a, that's my general requirements. B, hey Travis, good to see you, buddy. B is ambient temperature correction factors. So the ambient temperature correction factors, A1, you have an equation which lets you calculate based upon the ambient temperature if you so choose to do that. A2 is your rooftop adjustment. And remember, this went through some battles over a few code cycles ago. There were some studies done, and then their studies were undone. I don't know. All I know is what we got is adjustment factors for when you have conductors on a roof based on 86 correction factors when you have different ambient temperatures. So, rooftop. For raceways or cables exposed to direct sunlight on or above a roof, where the distance above the roof of the bottom of the raceway cable is less than 3/4 of an inch, so you're right on that roof, a temperature adder of 60 degrees Fahrenheit should be added to the outdoor temperature. So what they're basically saying is if you have them on a roof, you have them, say, in a raceway, and you're within less than 3/4 of an inch, and I'd say, maybe less than 3/4 of an inch. You don't have that air circulation around the raceway, so you add 60 degrees Fahrenheit or 33 degrees Celsius to the ambient temperature for the lack of that circulation. All right. And then you have in table 310.15b11 ambient temperature correction factors. And again, based upon 86 degrees. So if I expand this, I'm going to expand this table and try to show you this. Boom, 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 boom. So there's your ambient temperature. There's your 90 degrees C temperature rating of the conductor, 60, 75, or 90. And there's your 86, 78 to 86. And you'll notice the multipliers are 1.0. All right. And where am I looking? I'll show you where I'm looking. Whoops-a-daisy. There's your 78 to 86. And here are your multipliers. Or 1.0 for 90, for 75, and it's the same thing for 65. If I am if I'm at an elevated temperature, say I go up my multiplying factors. I don't know why it's doing that. Jeez, my multiplying factors go down. So I'm adjusting the ampacity of the conductor down. If my temperatures go lower, then I'm adding on to the ampacity of that conductor. So I'm basically adjusting my conductor ampacity based upon the conditions of use from a temperature perspective. So those are the ambient temperatures that we'll find. Hold on. Ambient temperature correction factors. Then there are adjustment factors in C. This is for when you have more than 3 current carrying conductors in a raceway. They give you the values that you would derate that conductor when you're exceeding that number. Okay, so we've got the ambient temperature correction. Then you have raceway spacing. Spacing between raceways shall be maintained. I think this, Jason, Doty, this is where you were talking about, it says spacing between, well, this is between raceways. That's not, you were talking about when you have multiple conductors in a cable tray. Then you have D is bare or covered conductors, where bare or covered conductors are installed with insulated conductors. The temperature rating of the bare or covered conductor shall be equal to the lowest temperature rating of the insulated conductors. You've got the neutral conductor. And you've got the grounding or bonding conductor. You know, Jason, I don't see anything in here that deals with in a cable tray. I don't see anything in here that deals with cable tray. That's a good freaking question. Willie Snyder says, isn't table 310.16 based on a 1,000 foot circuit length? I would say no, it doesn't matter the circuit length. Remember, it's the amount of current that conductor can handle, can carry. If I have, 10,000 feet of conductor, I'm carrying, whatever that ampacity is, I can carry that current through the conductor, because the what I'm worried about is heating enough to melt the insulation. Now, if I have lower voltages, which will demand higher currents, now I could exceed the current. But if I have 2,000 feet of conductor, and in that 2,000 feet of conductor, I'm let's take 310.16. Say a 2-watt conductor, 90 degrees C. 2-watt conductor at 90 degrees C can handle 195 amps. Whether that conductor is 1,000 foot, 2,000 foot, or 3,000 foot, I can handle 195 amps. Now, because of the voltage drop, I may have to increase my voltages, which may drive more current. I don't know. 310.15 C1, cable tray. 310.15, 310.15. I may have missed it. I thought I went through it. A, B, boop, 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 C1. There we go. Where conductors are installed in cable trays, 392.80 shall apply. Good catch. See that, Chris? I'm telling you, Laura, you're awesome. Why can't I get to 392.80? 392.80, ampacities of cables rated 2,000 volts or less in cable tray. You have multi-conductor cables. You have single conductor cables. The ampacity of single conductor cables are permitted. The adjustment factors shall not apply to the ampacity cables tray. All right. 310.15 C1 is your cable tray, and it's pointing you over. So, Jason, for cable tray, I would go to 392.80. And that deals with multi-conductor cables and then single conductor cables. You've got a lot of details there, a lot of references. Wow. There's a lot of pointing back to 310.19, 310.15. So I can see how that can get confusing. And you know what we might do? We might do a cable tray discussion and just focus in on that. It'd be great if you had some examples. We could work through those examples. Awesome. Awesome. Okay, 310. All right, so we went through in 310.15 the adjustment factors. Just make sure I got all of them. 310.15. Then 310.16 is your table. Now, the other thing we got to remember, the other thing that we must remember is that in 110.14, we already talked about a little bit the equipment that I'm landing the conductor in, this is where I argue is the circuit ampacity. And the ampacity of the circuit shall be limited or adjusted by the overcurrent. No, so here's my suggestion there, Felix. My suggestion is we worry about the overcurrent protection later. Remember, the equipment, the 75 degree C does not mean you always have an overcurrent protective device. My 75 degree C could be a terminal block, or it could be a transformer with no overcurrent protective devices in it. So just because I have the 75 degree C and I'm limiting it based upon the equipment is not necessarily because of the overcurrent device. The overcurrent protective device, after I've established the ampacity of my circuit, then my overcurrent device has to make sure I protect the circuit at that ampacity value. And then that may cause me to change the size of the conductor, because my overcurrent protective device always has to be 125% of the continuous load plus the non-continuous. And we're going to run through an example to demonstrate that. It's 1237. All right. Boom, 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 boom. Okay, 110.14c is your temperature limitations. It says the determination of temperature provisions of equipment shall be based on C1A or C1B, right? And then if I go to C1, equipment for circuits rated 100 amps or less, that's marked 14 through 1. That's 60 degrees C. And your motors marked B, C, or D is 75 degrees C. Equipment for circuits rated over 100 amps, larger than a 1 gauge, that's 75 degrees C. And motors marked B, C, or D is still 75 degrees C. Now here's my example. And I'm going to run through this example. I'm going to do two things. I'm going to run through it with these conditions of use. 4 current carrying conductors, 120 degrees Fahrenheit ambient, and my conductors have a 90 degree insulation. We're going to walk through and determine the ampacity and the protection, Felix, for this conductor. Then we're going to change the conditions of use so I'm not adjusting the ampacity of table 310.16. It'll be 3 current carrying conductors in the raceway, only 3 current carrying conductors in the raceway, and an ambient of 86 degrees, okay? But still have a 90 degree C insulation. So we're going to do this example twice, 2 different ways. Let's first do it based upon, which I would say this is the most complicated. This is a branch circuit, so I'm going to go to Article 210 for branch circuits. 210.19 tells me what the minimum ampacity and size is for the conductors. The branch circuit conductors have to have an ampacity not less than the larger of 2 calculations. So I'm going to do 2 calculations. So my process is going to be to determine the size based only on 1.25 times the continuous load plus the non-continuous load. Then I'm going to determine the size based only on the conditions of use. I'm going to select the larger of the 2. Then I'm going to evaluate that selected conductor per 110.14, which ensures the ampacity of the conductors is not greater than the temperature rating of that equipment. And then I'm going to select the overcurrent protective device. So I'm going to do all steps 1 through 4 before I even get to overcurrent protection. My overcurrent protection doesn't even enter into the debate and argument until the very last step. All right? So the first step is what conductor size can handle 125% times the continuous load plus the non-continuous. And in this case, I've got 88 amps. And this is a Back to the Future, I think it was 88 miles an hour, right? 88 amps of continuous current, so 1.25 times 88 amps is 110 amps. So I know for the first calculation, I need a conductor that can handle 110 amps. And I'm going, since I have a 90 degree C insulated conductor, I'm going to use the 90 degree C column, and I've got to get to a number that is greater than 110 amps, which gets me to a 3 gauge conductor. So a number 3. So now I know I got a 3 gauge copper conductor, can handle 110 amps. That's my size. So then I do the second calculation. which is an ampacity not less than the maximum load to be served after the application of any adjustment or correction factors. I'm not doing the 1.25. So now I've got I've got 4 current carrying conductors, so I'm going to adjust by 80%. And I'm at 120 degrees Fahrenheit, so I'm at a 90 degrees C insulation, so I'm at 0.82. So those are my two numbers. The first one is my 0.8. The second one is 0.82. I take my 88 amps, I divide that by 0.8, divide that by 0.82, and I have 134.15 amps. My conductor ampacity that I select has to be greater than or equal to 134.15 amps. So what conductor gets me that? That's my 90 degree C column. I go to a 1 gauge, gets me to 145 amps, which is greater than 134. I can't pick a number 2 because that's only 130 amps. So I need to be able to handle that 134.15 amps, which is a 1 gauge conductor. So now I'm at a 1 gauge copper conductor. And then I have to pick the larger of the two. So in the first calculation, I did a 3 gauge. In the second calculation, I did a 1 gauge. So now I am at a 1 gauge conductor. The larger of the two is 210.9 per 210.19 is the 1 gauge. So now I've done 1, 2, and 3. Now I'm at step 4. Evaluate the selected conductor for the equipment within which I'm terminating at. Now I know I have 90 degrees C and 75 degrees C. The weakest link is 75 degrees C. So I'm going to base the rest of my discussion off of 75 degrees C, not 90, because 75 is the most limiting factor. So I have a 1 gauge copper conductor. It can carry 145 amps based upon the 90 degree C column. The ampacity based upon the conditions of use is 95 amps. 95 amps is still greater than 88. So I can still carry that 88 amps, but not the 110 of the continuous use amps. The 110.14 termination for 75 degrees C can handle up to 130 for a 1 gauge conductor. The circuit ampacity has to be greater than or equal to 110 amps. 110 amps is less than the value in the 75 degree C column, which is 130 amps, and the calculated ampacity of the 1 gauge conductor, and it meets the requirements for 110.14. Does that make sense? Anybody disagree that I can put a 1 gauge just based upon those numbers? All right. So there's my 1 gauge, there's my 130 amps at 75 degrees. Now, so now I'm at a 1 gauge. So that's my final, is I'm at a 1 gauge conductor. Now I have to think about protecting the conductor. All right. Now I'm going to select my overcurrent protective device. To do that, I have to be able to protect the 1 gauge conductor. 210.20 tells me that I can that the overcurrent device has to be at least 125% of the continuous current. And the continuous current is 88 amps, so 1.25 times 88 is 110. 240.4b says I can go to the next larger, right? All right. And we know the ampacity of the conductor is 95 amps. So the next higher from 95 amps is 100 amps. So I based upon 240.4, I should be able to go to 100 amps on that conductor. But then the next question is that 100 amps has to be greater than 88 times 1.25. And 88 times 1.25 is 110 amps. So I can't use a 100 amp breaker. I'd have to go to a larger breaker because I need to at least be 125%. And if I go to a larger breaker, that means I need to increase my conductor size. So I have to increase the conductor to a 1/0, which is the next larger size. The ampacity of a 1/0 at the 90 degree is 170. I do my multiplying factors. I get 111.52. 1.25 times 88 is 110. So if I put a 110 amp circuit breaker on a 1/0 conductor, then I'm golden. 110 amps is not less than 125% of 88 amps. And it's greater than, it's less than the ampacity of the conductor, so I'm protecting the conductor. So I would say that's the smallest breaker. I could go to the next larger. If it's 111, I can go higher, but I wouldn't do that from a cost perspective, right? I would stick with a 110 amp breaker because I've only got 88 amps of load. Jason Doty says, I'm just reading your note, Jason. 240.4b conditions 2 and 3 are typically met. Condition 1 may have an impact. 240.4, I gotta look at 240.4b. 240 is overcurrent protection. 240.4, 240.6, 240.5, 240.4b, overcurrent devices rated 800 amps or less. Yeah, conditions 2 and 3. The ampacity of the conductor does not correspond with the standard ampere rating. Yep, and the next higher does not exceed 800 amps. Yep, and it says, and you're saying that condition 1 can have a massive impact. The conductors being protected are not part of a branch circuit supplying more than one receptacle for cord and plug connected portable loads. So yeah, that's a very good point, Jason. If your conductors are not part of a branch circuit supplying more, so the next higher standard overcurrent device rating shall be permitted to be used provided all of the following conditions are met. So condition 1 is the conductors being protected are not part of a branch circuit supplying more than one receptacle. In this case, I'm not a part of that, and I would agree. So if you have more than one receptacle for cord and plug connected portable loads, then you're right. That's a killer right there. Good point. Very good point. All right, so I'm at a 1/0 conductor. I'm at a 110 amp breaker, and I think that I'm good. A 1/0 conductor, 110 amp breaker. I could go to the next higher, the next size up breaker, but I would be foolish to do that unless I had a tripping issues. The equipment may have an inrush current or something. Whatever, but that 110 amp breaker would suffice for this application. It exceeds 125%, or it's equal to or greater than 125% of the 88 amps. It's less than the ampacity of the conductor, and we're good to go. So that's that circuit. So now what I want to do is I'm going to say, let's change the conditions of use. What if I don't have that complicated? What if it's simple? 3 current carrying conductors. I'm at an 86 degree Fahrenheit ambient, so 78 to 86. That's going to be a 1 multiplier, 100% multiplier based upon the ambient temperatures. I'm going to go through the same process. I'm going to do both calculations. I'm going to do based only on 125% of the continuous plus non-continuous. I'm going to determine the size based only on the conditions of use. Select the larger of the two. I'm going to evaluate the selected conductor per 110.14, thinking about both ends of the conductor. Make those adjustments, and then I will have selected my conductor, and then I got to make sure that I can protect that conductor and make sure that the overcurrent device is greater than or equal to 125% of the continuous plus non-continuous. All right, so we're going to do that. This slide doesn't change. It's the same as the same as the same. 88 times 1.25, 110 amps. I go to the table, 115, 3 gauge conductor is good to go. So there I am, 3 gauge copper conductor. The next step is going to be establishing the conditions of use, which I don't have to apply this because I'm at 3 current carrying conductors. This is a 1.0 multiplier because I'm around 86 degrees Fahrenheit, so I'm not adjusting, I'm not correcting the ampacity based upon ambient. So 88 over a unity is 88 amps. So the ampacity of my, or the load that I need is 88 amps, and the conductor ampacity has to be equal to or greater than 88 amps. I can use a number 4, a 4-gauge conductor for 95 amps. I can't do a number 6 because that's only 75. 95 would exceed the 88 amps. All right, so now I know I'm at a 4-gauge conductor. I haven't picked my overcurrent device yet, and I have to do the comparison of the two, a 4 or a 3. 3 is larger than a 4, so I'm going to go with a 3-gauge conductor as my larger of the two. So I've done 1, 2, and 3. I'm at a 3. I'm at a number 3. Now I've got to think about 110.14. I know, again, I'm at 75 degrees C. So a 3-gauge copper conductor carries 115 amps based upon the 90 degree C column of table 310.16. A 3-gauge copper conductor ampacity is 115 amps because I'm meeting all the conditions of use of table 310.16. 110.14 tells me for the 75 degree C column, that 3-gauge conductor I can only have 100 amps for that circuit, for the circuit ampacity. The circuit ampacity has to be equal to or greater than 1.25 times 88, or 110. My 110 amps is less than the ampacity of the 3-gauge conductor, but greater than the ampere value in the 75 degree C column for the 3-gauge conductor. So I can't use a 3-gauge because a 3-gauge conductor landed in 75 degree C equipment can only handle 100 amps. I need 110 amps. So I have to go to the next larger conductor, which is a number 2, which can take 115 amps in the 17 degree C column, which is greater than my 110 amps. So I'm good to go with a number 2. There's my number 3 can only handle 100, but I need 110. I increase the size of the conductor to a number 2. I can handle 115. So, what was that up there? See, that's screwed up. I got to change that. What's in the red box is incorrect. That up there is, I copied this slide. So let me do this. I'm going to fix it right now. I'm going to fix it. Boom, ba bum, bum, ba 75 degrees C. 3-gauge conductor. 3-gauge conductor ampacity is 115 amps. 115 amps. Based on conditions of use. 115 amps. Right. I'll leave that in there. Based upon conditions of use, which is 3 current carrying conductors, blah, blah, blah. So I'm just going to copy this, Control C, go to the next slide, Control V. All right, so hit save. Okay, so now I'm at a 2-gauge copper conductor. Let me go back. Yep, okay, so I'm at the 2-gauge. I lost my train of thought. I'm at what the heck? Look at this. I'm in the wrong one. All right. Hopefully you guys were seeing all of that. Anyway, all right. So let me go back. All I did was I changed the red. I don't know what you saw of that or not. I wasn't looking. So I changed that red box to have 3-gauge copper conductor ampacity is 115 amps. All right, so based on the impact of the selection of 110.14, the conductor size is increased to a 2 gauge. So now I've done 1 through 4. I know I'm at a 2 gauge. Now I have to protect that conductor. So what the ampacity of that conductor is 100. Why do I have 130 amps? What's the ampacity? 310.16. The ampacity is 310.16. Come on, people. The ampacity, expand table, of a 2, okay, yeah, 130 amps, that's 90 degrees C. Nope, that's wrong. That is wrong. So my ampacity of this circuit is technically 115 amps, right? OCPD selected must be adequate to protect the 1 gauge copper conductor at its ampacity. 210.20 tells us that OCPD must be at 125, blah, blah, blah. 240.4b tells us that. So 115. 150 amp, 115. So if I have 115 amps, that means based upon 240, 240.6. I'm going to go to 240.6, up the table, 240.6a, 115. The next higher is 125. So 125 amp. Let's check that. 125 amp. Overcurrent device is permitted based on 240.6. Okay, is greater than 125% of the continuous, but is that, so 125 amps, 125 amp, so let's go 125. Whoa, baby. 125 amps, there we go, 2 gauge, ampacity of that circuit is 115. I got to protect it at its ampacity, 125. Is the next higher is permitted based on that. For an ampacity of 115 amps, 125 amp is permitted. We know that. 210.20a requires that the rating of the OCPD not less than the non-continuous plus the continuous. Right? And that is 1.25 times 88 amps is equal to 110 amps. Right? So 125 is greater than, so I'm good there. So right, so the circuit breaker as small as 110 amps, that's true, as that would not be less than 125% of the continuous. So that could be, I'm going to change this to 125. And this is going to be, what was this, 115? 115. 1.25 is 110. A 125 amp breaker is permitted because the rating of the OCPD is greater than 1.25 times blah, 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 blah. So 125 amps, but I could go down to a smaller breaker. I can go down to a 110 amp breaker on that circuit if I wanted to. So I'm picking a 2 gauge copper conductor and 3 current carrying, 78, blah, blah, blah. I've done everything in my power for that application. Okay, so we went through the conditions of use. We picked The conductor ampacity, we lowered that based upon the equipment that we were terminating in. And then we selected the branch circuit over current protective device to provide the protection. All right, so let's take a look at some of the comments. 240.4b condition, we already talked about that. I remember when Crystal Hunter taught me that a wet location conductor with -2 is 90 degrees C in both wet and, yep. And we get that from the table. So, so if we go to 310, David, remember, is it throw? Here's our table right here. So let's look for a -2. There's a -2 right here. RHW -2, 90 degrees C, dry and wet. RHW without the -2 is 75 degrees C, dry and wet. Let's look for another -2. Here we go. THWN, dry and wet location, 90 degree, 75 degrees C. There's a lot you can learn from this table, which is table 310.41. So, you know, studying some of these applications and studying the tables can teach you a lot when you start to, you know, investigate a little bit more and more. All right, Laurel, thank you. And we got through some of the major stuff. Jason, we didn't get too detail on the cable tray, but I'll prepare something for cable tray specifically. So hopefully you guys got something out of our discussion today about ampacity. We've got, I like to think of it from a conductor ampacity, just based upon the terminology, conditions of use. And I like to think of the circuit ampacity as being something different. I've got the ampacity of the conductor and then the ampacity of the overall circuit, which includes what I'm terminating in. All right? All right. David Engelhart, Jason Doty, Felix Sandoval. We've got Colombia represented. We've got Egypt represented. We've got Florida represented. I'm sure there's suddenly be somebody from Texas. We got Weird and West by God, Virginia represented. Laurel's out there. I think, Laurel, are you in Wisconsin? I'm not sure. I can't remember. Laurel, where are you at? Thank you, Don Ganir. Have a great rest of the day. I hope everybody had a great 4th, regardless of what country you're in. You had a 4th of July. I hope it was a good day for you. All right, Steve, thank you very much. Thank you very much, Steve. I appreciate it. And hopefully we added some clarity. So, Nebraska. Thank you, Laurel. Thank you, and thanks for your research and for all of your help and everything that you do. And same goes to everybody else out there. I appreciate the engagement, the dialogue. Don't forget to subscribe, like, hit the thumbs up. And if you hit the thumbs down, you got to do it twice. If you hit the thumbs up, you could do it once or 3 times. Odd numbers hits, even number hits. All right. Thanks, everybody. Take care. We will see you next week. Am I going to be live next week, or do I have to record one next week? Let me double check-lay. Tuesday of next week, I might be able to go live. So hopefully we will see you live. Thanks, everybody. Take care. Stay safe. God bless. And please stay healthy. Do what you can do. Yeah, 18 watchers and only 4 likes. Come on. Hit the thumbs up. Come on. All right, everybody. Take care. Thanks, Don.